Three identical spin half fermion are to be distributed in two non-degenerate distinct energy level. The number of ways this can be done. Solution. We have according to, let us make a table, then we will write down the statements. It is energy level E1, E2, particle state, first, second, third. ठीक है, let us 1, 2, 3, 4. According to Pauli exclusion principle, no to fermion having same quantum number, having same quantum state, can present in the same energy level. So let us write it down. We would be having 1 by 2 minus 1 by 2 and 1 by 2 here. We would be having 1 by 2 here, 1 by 2 and minus 1 by 2 here. We would be having it 1 by 2 minus 1 by 2 and minus 1 by 2 here. We would be having it minus 1 by 2, 1 by 2 and minus 1 by 2 here. So the number of ways this can be done is 4. Our answer for this problem is option second, value 4. We are discussing the CSIR NET Physical Science December 2013 problem of quantum mechanics. This is a 3.5 marks MCQ. Let us read the statement of this problem. A spin half particle is in the state chi is equals to 1 by root 11, 1 plus I by 3 in the eigenbasis of s square plus s square and sz. If we measure the sz, the probabilities of getting plus h cross by 2 and minus h cross by 2 respectively are. We have to determine the probability of finding the particle in sz eigenbasis for plus h cross by 2 and minus h cross by 2. So solution would be the spin half particle is in the state 1 by root 11, 1 plus I by I 3 in the eigenbasis of s square sz, re-expressing the wave function in terms of spin up and spin down eigenvectors. Chi would be 1 plus I by root 11 equals to 1 by 2 into 1 by 2 plus 3 by root 11 into 1 by 2 minus 1 by 2. Here we have used 1 by 2 state as 1 0 and 1 by 2 minus 1 by 2 state as 0 1. The probability of getting positive h cross by 2 is P is equals to positive h cross by 2 to mod 1 by 2 chi square would be 1 plus I by root 11 into 1 by 2 to 1 by 2 square equals to 2 by 11, and similarly the probability of getting minus h cross by 2 is P equals to minus h cross by 2 equals to 2 minus 1 by 2 of chi equals to 3 by root 11, 1 by 2 minus 1 by 2 into 1 by 2 into minus 1 by 2 mod square equals to 9 by 11. Thus, our correct answer would be option second, 2 by 11, 9 by 11 for this problem. The motion of a particle of mass m in one dimension is described by the Hamiltonian p square by 2m 1 by 2m omega square extra square plus lambda x. What is the difference between the quantized energy of the first two levels? In the following, delta x is the expectation value of x in the grounded state. So here in the answer this term represent average of x. Solution. We have h is equals to p square by twice m plus 1 by 2 m omega square x square minus lambda x. This can be written as p square by twice m plus half m omega square, and here we would be having it x square minus 2 lambda x by m omega square. So we would be adding it up, lambda by m omega square plus minus lambda m omega square, subtract, adding and subtracting this term. So what do we get? We get h is equals to minus h square by twice m t square by del x square plus half m omega square to x minus lambda by m omega square का whole square minus lambda square by 2m omega square. Now we define y is equals to x minus lambda by m omega square implies del by del x is equals to del by del y. So our h would be minus h square by twice m del square by del y square plus 1 by 2 m omega square y square minus lambda square by 2m omega square, which can be written as h naught minus lambda square by 2m omega square, where h naught is defined as minus h square by twice m del square by del y square plus half m omega square y square. The energy eigenvalue corresponding to this Hamiltonian is En is equals to n h n would be n h naught minus lambda square by twice m omega square and h naught and lambda square by twice m omega square and so this term would give us n plus half h cut omega minus lambda square by 2m omega. The ground state energy of the particle is E0 is equals to 1 by 2 h cut omega plus lambda square m omega square 2. The excited state energy of the particle is E1 is equals to 3 by 2 h cut omega minus twice m omega square. The difference in the two energy level is delta E is equals to E1 minus E0 equals to h cross omega. Thus, our answer for this problem will be option 4. Let psi NLM denote the eigenfunction of a Hamiltonian for a spherically symmetric potential VR. The expectation value of LZ in the state psi, which is a linear combination of state 200, 210, root 210 and 211 is. So we have to determine the expectation value of LZ. Solution: we have psi is equals to 1 by 6 psi 200 plus root 5 psi 210 plus root 10 21 minus 1 plus root 20 211 and psi dot psi is equals to 1. So that is our given statement. The possible measurement of LZ and their probabilities are R. So for first term, LZ would be 0 and probability P of bracket में LZ equals to 0 would be 1 by 36. That is from first term. From second term, LZ is equals to again 0. Probability P of LZ is equals to 0 would be 5 by 36. ठीक है. From third term, LZ1, LZ2, LZ3 is equals to minus H cross and probability 1 to probability P3 LZ is equals to minus H cross would be how much? 10 by 36. And from fourth term, LZ4 is equals to, that is Z, positive H cut and probability P4 LZ is equals to positive H cut would be 20 by 36. Now the expectation value of LZ is given by P1 LZ1 plus P2 LZ2 plus P3 LZ3 plus P4 Z4, that is 1 by 36 into 0 plus 5 by 36 into 0 plus 10 by 36 into minus H cut plus 20 by 36 into positive H cut, and average LZ will turn out to be 10 H cut by 36, which is equals to 5 H cut by 18. So our answer for this problem would be option 4, 5 8 by 18 H cut. If psi x is equals to a e की power minus x की power 4 is the eigenfunction of one-dimensional Hamiltonian with eigenvalue e is equals to 0, the potential Vx in unit where h cross is equals to 2m is equals to 1 is. We have to determine the approximate nature of the potential. Solution. We have psi is equals to a e की power minus x की power 4 and e is equals to 0 and h is equals to h cross is equals to 2m is equals to 1. This Schrödinger equation of motion for the particle which h psi is equals to E psi implies minus h cross square by twice m dl square psi by dx square plus v psi to E psi. Substituting the given values of psi, E and h cross and 2m in Schrödinger equation, we get del square minus psi by del x square plus v psi is equals to 0 implies v psi is equals to del square psi by del x square, that is implies va e to the power minus x to the power 4 equals to a del square by del x square e to the power minus x to the power 4. That means va e to the power minus x to the power 4 is equals to a to del by del x minus 4 x cube e to the power minus x to the power 4. That means a e to the power minus x to the power 4, we will be having 16x to the power 6 minus 12x square. X square, or the potential V is equals to 16x to the power 6 minus 12x square. So our option 4 is the correct answer for this problem. A particle is in the ground state of an infinite square well potential given y vx is equals to 0 for region minus a to a and infinity otherwise. The probability of finding the particle in the interval between minus a by 2 and a by 2 is. So we have to determine a probability between this region. Our solution. We have Px is equals to 0 infinity for minus a x as in a otherwise the energy and value and corresponding eigenfunction of the particle is given by for the potential for the pot, for the potential given above are E1 equals to pi square h cross square by 2m to 2a square psi is equals to root over 1 by a cos pi x by 2a. The probability of finding the particle in the interval between minus a by 2 to a by 2 is given by E is equals to minus a by 2 to a by 2 psi star psi into dx, that is 1 by a minus a by 2 to a by 2 cos square pi x by 2a pi x by 2a, not pi x by a, dx. This integration can be solved by 2 by a 0 to a by 2 cos square pi x by 2a dx, or one can write 1 by a into 0 to a by 2 1 plus cos pi x by a dx, which gives us 1 by a into x plus a by pi sin pi x by a 0 to a by 2. So value is 1 by a 1 upon 2 plus a by pi sin pi by 2. Here a by 2 would give us 1 by 2 plus 1 by pi. Thus our answer for this problem would be option 2, 1 by 2 plus 1 by pi. The expectation value of x component of orbital angular momentum Lx in the state psi is equals to 1 by 5 root 3 psi 2 1 minus 1 root 5 2 1 0 minus 11 2 1 plus 1, where psi and Lm are the eigenfunction in usual notation is. So we have to determine average Lx. Solution. We have psi is equals to 1 by 5 root over psi 3 2 1 minus 1 plus root 5 psi 2 1 0 minus root 11 2 1 positive 1. Further psi dot psi is also equals to 1. The operator Lx in terms of dagger in terms of ladder operator is expressed as Lx is equals to L plus L minus by 2. Now let us determine L plus L minus separately. So L plus operating on psi would be 1 by 5 into L plus straight to 1 minus 1 plus 3 plus root 5 to 1 0 minus root 11 to 1 1. So here 1 by 5 L plus 3 to 1 minus 1 plus root 5 L plus 2 1 0 minus root 11 L plus 2 1 1. So what do we get? We get from here 1 by 5 3 root 2 h cut into straight to 1 0 plus root 5 into root 2 h cut to 1 1 minus 0. So 1 by 5 is equals to 3 root 2 h cut to 1 0 plus root 10 h cut to 1 1. Now multiplying brown on the left side, so psi would be equals to 1 by 25. Now we would be having it 210 state would be 3 root 10 h cut into 210 by 210 plus here we would be having root 10 h cut. So 211 state would be with minus sign minus root 11 into root 10 h cut 211 into 211. So we got result 3 root 10 h cut divided by 25 minus root 11 into root 10 h cut divided by 25. Similarly, let us calculate average LZ. Average L minus. Now L minus is operating on psi. We would be having 1 by 5 L minus 3 straight to 1 minus 1 plus root 5 to 1 0 minus root 11 to 1. Now, so our result would be L minus psi would be 1 by 5 3 L minus 2 1 2 minus 1 plus L minus, here I would be having root 5 L minus 1 210 minus root 11 211. Now if we apply it, so what do we get? We get 1 by root 5 3 into 0 plus here we would be having root 5 root 2 h cut, and here our state would be 2 1 minus 1. Here our is root 11 into root 2 h cut, state would be 2 1 0. We can write it as 1 by 5 root 10 h cut 2 1 minus 1 minus 11 into root 2 h cut 2 1 0. L minus psi. Now multiplying with brow of psi, so L minus psi would turn out to be 1 by 25 root 10 h cut into 3 2 1 minus 1 into 2 1 minus 1 minus of minus root 11 into root 10 h cut 210 into 210. So our value turned out to be 3 root 10 by 25 h cut minus root 11 into root 10 by 25 h cut. So average Lx is given by, now one can check it out. What is the value of average L plus? L plus is 3 root 10 by h cut 25 minus root 11 by 10 into 25 h cut. ठीक है जी. So similarly, what is the value of average L minus y? 3 by root 10 h cut by 25 root 11 into root 10 by 25 h cut. That means L plus is always equals to L minus. I would have done it directly, but to show it here, I have go through the rigorous calculation. Now this condition is always valid so long as there is no exponential term in wave function. If exponential term is there in wave function, then we have to do the similar method again. So average Lx would be given by average L plus L minus by 2, which can always be written as average L plus, and average L plus was, I can take it root 10 by 25 h cut outside. So we would be having it what? With minus sign, we would be having it root 11 minus 3. So thus our option A for this problem is correct answer. A particle is prepared in a simultaneous eigenstate of L square Lz if L, L plus 1 h cross square and M h cross are respectively the eigenvalue of L square Lz, then expectation value of Lx square of the particle in this state satisfies. Solution. We have average L square would be equals to Lx square plus Ly square plus Lz square, which can be written as Lx square plus Ly square is equals to average L square minus average Lz square. Further, we know that that average Lx square is equals to Ly square. Substituting this in above equation, we get average Lx square is equals to 1 by 2 average L square minus Lz square, which can be written h square by 2 into L plus 1 minus ml h cross. Lx square will be minimum when ml is maximum, that is ml is equals to L. So in that case Lx square would be equals to h square by 2 into L plus 1 minus, here it is square L square, so and h square I have taken outside, so this would be there. So this term would be equals to LH square by 2. Lx square will be maximum when ml is minimum, that is ml equals to 0. So average Lx square in that case would be equals to r by 2 into L plus 1. So this condition is satisfied in option D. Thus option D is our, or option 4 is our correct answer. A perturbation V perturb is equals to A L square is added to the hydrogen atom potential. The shift in the energy level of the 2p state when the effect of spin are neglected up to second order in A is. So we have to determine what is the shift in 2p state. Solution. We have H dash is equals to V perturb equals to A L square, implies E would be equals to A H cross square into L plus 1, where we have used L square is equals to L plus 1 H cross square. Now for 2p state, L is equals to 1. The shift in 2p state is given by E is equals to A H cross square 1 into 1 plus 1, that is 2A H cross square. So for this problem, our option 3 is correct.